postpone it till Monday because a lot of people aren't going to be here. They told me that. So we'll just do it on Monday. Any questions, go ahead, Jay. Or Lydia.
I have a question. Yesterday when we were solving on that Smith chart, I can't figure out where we got one of the values from.
How about this? Why don't we do that problem and get your calculators out, and if you have a rotated Smith charts, you don't have a rotated?
The one that you had up on
Yeah, that's
this one.
I'm sorry. Do you have a compass with you?
Yes.
You can draw a rotated. The only thing you do is put this right in the center there of this one, get the radius of the one circle, take it over to the center there and do it. But you can redraw that, and you got a nice Smith chart there too. That's a good one. But I want to just take you through it. So we're going to do problems, three kinds of problems. One is where once we normalize, the value of z normalized is inside that one circle. So that one, we've got to add a parallel element first, so we go to the admittance domain. The second one is we're going to find one where the normalized impedance is inside the rotated circle. Y'all with me on this? That's the one that's rotated. And show you how to do that problem. And the third thing we're going to do is one where the impedance is outside of both of those. Go ahead, Jay.
I just had a quick conceptual question. So you know how the skin depth becomes a big problem with transmission lines, normal transmission lines?
Well, skin depth isn't a problem with transmission lines. Skin depth is the current hugs the surface of the conductor.
Doesn't that increase resistance quite a bit?
It can, and this is the thing, copper's resistivity is extremely low. I mean, its conductivity is very high. So even with a small skin depth, remember we were calculating AC resistances and stuff? At gigahertz frequencies, the line losses are trivial. It might be a half of ohm, a quarter of ohm, but your characteristic impedance is 50 ohms, so you don't worry about that. But we'll go through it. Go ahead. Or this problem, give it to me again. What is the number?
I'm just going to give you the problem from the homework.
Yeah, which is there a number on it or not?
No, this is just one you wrote out.
Go ahead.
It says ZL is 100 plus J.
Oh yeah, and this is one where did y'all see that tool I gave you on there, the internet tool, where you can go and you can put in the values and then it looks for solutions, high pass, low pass. We haven't got to them or anything like that. The only thing you look for is that one that basically is the parallel series component. Do y'all see that, class? Did you see it or not? That tool is fantastic. Mark that. All right, ZL is 100 plus what?
J100.
Okay, and Z naught is 50?
Yes, sir.
All right, and you want this matched, right? We want to develop an L series matching up. Okay, now this is one of those things. Oh, you need the frequency.
It's 1 giga.
All right, 10 to the 9th hertz, which is nice. All right, that's really nice. So we know that the wavelength there is 30 centimeters, right? C over F, C is 310 times 10 to the 8th over F is 10 to the 9th. That's 3 times 10 to the minus 1 or 0.3 or 30 centimeters, right? 30 centimeters is what? Let's see, a meter is that long, 30 centimeters about that long, right? 30 centimeters seems fairly long, right? For a printed circuit board. So you don't have to worry. But when you get into larger electronics and you're going from power supply to antenna, probably everything goes into the domain where you better impedance match. Y'all follow me on this? So now, so the first thing we do is what? We get the normalized impedance, right? Load impedance, and that's going to be, I'll call it small ZL. That's just load impedance over Z naught. And that's 2 plus J2, isn't it? All right, now it's 2 plus J2. These are the markers that I brought down here stink. They were brand new, supposedly, but they're not. The second thing, we're going to draw a Smith chart, and I sketched these things freehand. You have Smith charts, but the way I do this usually is I put the one circle in, and everything else I know where it falls. So R equal 1, R equal 2 would be about here if you look, right? Take a look on your Smith charts. Can you all see that? All right, R equal 2. Now, I've got what? 2 plus J2. Well, I know J1 does this. That would be J1. This is about J2. You can correct me. It might be a little different. Do y'all agree with that? Roughly up there? Right? Jake, are you with me? So 2 plus J2 would be right here. This would be 2 plus J2, which is the normalized ZL. Everybody agree? Now hear me. Anytime we're doing impedance matching, the only thing we're going to add is an imaginary reactance. All right, it'll never change the real value. So here, if you look at this, if the real value is J2, if you take a look at this trajectory, everywhere I go around this orbit, where r equals 1, I can add or subtract some imaginary component and get rid of the imaginary term, right? I can make it 0, I can make it anything. But the problem is, no matter what I make it, I can't get to the one circle. And that r equal 1 circle is the place we want to be, because there we know if we get rid of the imaginary component, then the normalized impedance is 1, and that means Z naught is equal to the impedance you're going into. Do y'all follow me on that, class? With me on this? So, here's what we're going to do. No matter what we add in series, that would be an impedance, it'll never bring that to the 1 circle. So we have to go to the admittance domain. And we go, this would be point 1. So we go right through the center to point 2. And this is YL, this is 1 over ZL. And that, what is that? 0.1 plus J 0.1? You can correct me if I'm wrong. Is it? You got calculators, right? Do them. Just do it. Prove it to yourself. Is that right?
0.25.
Pardon me? 0. What did you say?
0.25.
Okay, I'm sorry about that. 0.25 plus J 0.25.
Minus.
Huh?
Minus.
Minus. Sorry. Yeah. Make sure you get that. Just take 1 over 2 plus J2. If somebody wants to do this long-handed, if I take 1 over 2 plus J2, right? And I wanted to find out what that was. Remember how to do this, guys? No? Anybody, do you remember how to get a real and imaginary? You multiply top and bottom by the complex conjugate, right? So I multiply top by 2 minus J2, right? And the bottom by 2 minus J2, correct? Y'all remember doing this? So you get a real and imaginary, but now on top you have 2 minus J2. And what do you have on the bottom? 2 times 2 is going to be 4, right? Then I have plus J4 minus J4, 0. And then I have J2 times J2, 2 times 2 is 4, J times J is minus 1, but there's a minus sign plus 1. So it's 4 plus 4, or 8, right? Well, 8 over 2 is 1/4, or 0.25, and that's 0.25 plus, or minus, pardon me, minus J 0.25. That's how you do longhand if you had to. 99% of the time your calculators do this for you. If you want to, you can turn that into a polar number. It's even easier to do. So, now we have that. We get YL equals 0.25 minus J 0.25. And this is the question we ask. Now I'm going to have to draw the rotated circle. Now we're in the admittance domain. You agree? We came in impedance, now we're in admittance, we're adding in parallel. Now we've got to see what kind of normalized admittance we want to add. So if I go here, right, there's 2 ways I can go. Just listen to me. Remember that that's the one, this is 0.25. So if you looked at the 0.25 large circle, it would be something like this, right? Something like that. You agree? Now, anytime we add reactances, we're going to increase or decrease that minus J.25. We could add this way and come to this point, correct, class? And here's the thing. If we're adding admittances, positive admittances are capacitor, positive J is capacitor, negative J is inductor, all right? Here's a tip. Anytime you're given that option, if it's an admittance component, a parallel component, always use a capacitor. In other words, plus J something. The reason is the capacitor blocks DC. All right, a capacitor will block any kind of short to ground that could happen. So what I'm going to do, I didn't draw this, but this is my ZL, 100 plus J 100. Here's my characteristic impedance, Z naught equal 50. The first component I'm going to add is parallel, and I'm going to just show you the admittance of it. So I'm going to go this way. Now, if you trace the article 0.25 circle, you're gonna come to this point, aren't you? This would be 0.3. This is where we're gonna add it in minutes. Do y'all agree with that? So what's the value up here? Can you guys look at your Smith charts? And just, you don't have, did you manage to draw rotated? You did, all right. So can you find 0.25 there? Because my eyes,
Just try this one.
is it right there? All right, now if you can go up, where does it hit this one circle, that faint
Just
line?
drawing a straight line or curved?
No. Remember, what you're gonna do is this. See, this is the article 1. When you add plus or minus j things, what you're doing is moving the trajectory up and down that. So if you can find out where it hits there, just give me the imaginary part. That would be out here.
So it'd be
It's gonna be it.
like 425?
Yeah. That's not
This
right.
is it what?
Plus 425.
0.25. Go ahead, plus j, say it again.
Wouldn't it be 1 because you're on the 1 circle?
No, I
You're on the
got
rotated
0
circle.
point.
Remember,
Oh.
we're at 0.25. Here's the thing we're on, right? That's the trajectory. We can add or increase the imaginary component, which means you're moving up and down here, right? This is not the 1 circle, it's the 0.25 circle, isn't it? Y'all with me on this class? The 0.25 circle is this big one. Y'all with me? This is can you see it, Lydia, or not?
Yeah, I'm good.
All right, so here it's 0.25 plus j, say it again. Okay, or Ashland, is it Ashland?
Yes.
What is that value up here for the imaginary?
0.425?
Can you confirm that, people? Hmm?
Yeah, 0.44.
425, 44, something like that. Depends on,
Yeah.
how well your Smith chart's rendering this thing. All right, now, you notice what happened. We moved from here to here. The real part doesn't change. I went from minus 0.25 to 0.425, right? That means I added what? Well, I added 0.245 plus 0.25, right? You all agree with that? With me? So that means this value right here is going to be a normalized plus j 0.425 plus j 0.25 because it was minus 0.25. And that's going to be what? J 0.675 you're going to add here, right? That would be the value you add. That's the imaginary component. You with me, class? With me? All right. Now I'm here. Now what do? I'm still in the admittance domain. What do? When I'm here, what do? I went from there to here, right, by adding the component. Now what?
Then you move.
I'm going to the impedance domain, right? I'm going over here. Correct, class? Lydia? All right, so that's 0.3. This would be 0.4. Now, I know that's going to have a real value of 1. It should be just about perfectly 1. Do you agree, class? But the imaginary component, I don't know. So what's the value right here? 1 minus j something.
So whenever we go to the admittance domain, we can't use this Smith chart. We have to use the rotated one. So would the values
Well, that is
be?
a rotated Smith chart. You got a rotated circle. Right? There's a
The-
rotated circle.
Okay. Yeah, I drew it.
Yeah,
but
that's
these
fine.
values.
Well, those are what? Mile markers. He's asking these values. These values are what? Those are the plus j values.
Yeah.
These values are the minus j. This is a road map. The only thing you're doing is that's the geolocation of that point. 0.25 plus j 0.425. Anywhere on this circle, we can find a point that defines it, right? Doesn't matter where you are. But I know if I can get on that circle, that's admittance. When I take 1 over admittance, I'm impedance. Now I'm in the impedance domain, and I have 1 minus j something. What's that minus j? Anyone?
I got 1.75, but that could very easily be wrong.
Minus j 1.75?
Yes.
All right. Well, here's how you do it. Take this value, 0.25 plus j .425, take 1 over that.
Because it's a factor. Yeah.
Huh?
I noticed, that's what I was gonna ask, because they're all just kind of off by a fact, like they're different by a factor of
What is
10.
different?
Like the left and the right side,
What left or right side?
of like these values, this is in the same place as like that value, the 5 and 0.5, but it's just changed by a factor.
These are degrees you're looking at, aren't they? I mean, the J's
The J's,
do
that's
this.
what I'm talking
This is J1, this is J like 2, 3, 4, 5, and so forth. See that? This is J.25 and stuff down here.
Yeah.
And finally, J is 0 at the equator.
Yeah. I was just.
All right, what did you get for this? Just take 1 over this value, 0.25 plus J.425. Anyone? You got a calculator? No?
I got 1 minus J 1.75.
Okay, that's 1.75. Now, here's what I think Lydia and Harmony got, that value. Is that what you got?
Yeah, that's what I got.
That's right. Now we're in the impedance domain. So we're going to add a normalized impedance. What's the value of the normalized impedance? Just look here. What does it have to be? If we want to get rid of minus J 1.75. We add plus J 1.75. Correct, class? Y'all say it? So I just add J 1.75 right there. This one's J 0.675. Right? And that's admittance, that's impedance. They're both normalized, correct? Yes?
I missed how you said to check that. I know you said to add 2 numbers and divide by it, but what 2 numbers do you add to check the 1.75?
I didn't add 2 numbers to get that. I added 2 numbers to get this. Right? I was here, right? I add 0.25 minus J 0.25, right?
Mm-hmm.
Well, the 0.425 is where I want to be, right?
Mm-hmm.
So I know I went from 0 to 0.425, right? Plus what? I had to go 0.25 to get rid of this minus J 0.25. So I said I have, my values here would be 0.25, that's where I started, right? I add that much, I'm back to 0. Then when I add 0.425, now I'm right on the rim there. You with me?
Mm-hmm. Yeah, I'm good.
So now when I'm on the rim there, I add the impedance, right? It's positive, this is positive, and now I'm done. Except for one thing, this is in the impedance domain, it's normalized, this is in the admittance domain. So now I have to get the actual values of the components, correct, class? Is everybody with me on this one? All right, now, how do we get the components? We'll start with the admittance. We have a value that we have to render of J 0.675, right? It's normalized. So I say I have plus J 0.675, and that's the normalized admittance of this element. I'll just call it, I know Dr. Wentworth uses B and stuff. I'm just going to call it Y. Right? Y is usually a symbol for admittance, correct? All right, well, what is that? Well, first think about impedances and resistances. Impedance of a capacitor is 1 over J omega C, correct? There's nothing tricky about this, right? Y'all know that. If I take that and divide it by, or normalize it, remember everything we've got over there is normalized, so I have to normalize it, divide by Z naught. Now I have that, right? With me? That's equal to this. Just set it equal. Well, I'm sorry. This is the normalized impedance, right? But we want admittances 1 over Z normalized. This is unnormalized, so we have J omega C Z naught. That's 1 over the impedance is the admittance that's normalized now, correct, class? We set that equal to this. J 0.675, and therefore we can say that C itself, the J's go away, would be equal to 0, right, 0.675 divided by omega divided by Z naught, and for ours it would be 0.675 over 2 pi times 10 to the 9th, right, in hertz, times Z naught, and Z naught was 50. So this is the value we should get. Can you give me that value, anyone?
2.15 picofarad.
2.15 picofarads?
Yes, sir.
Y'all agree? All right. That's the capacitor. What about the inductor? How do we get the inductor? We'll do it here. We'll think. We've got the normalized value of impedance, right? 1.75, right? So we have J 1.75 over here. That's normalized. That's impedance. What has an impedance of plus J something? An inductor, right? An inductor has an impedance of J omega L. Do you all agree with this? All right. So we set it equal to J omega L. And what do I have to do? Normalize. Divide that by Z naught. Exactly. Now you can see that L here would be equal to 1.75, right? Times Z naught over omega. Or L is equal to 1.75 times 50 divided by 2 pi times 10 to the 9th. And can you give me that value? Looks like nanometers. Anybody?
13.9 nanometer.
Can anybody confirm that? Class? The more you use your calculators usually in class, the better off you are. Is that right? All right, now look at and see the solution I posted. What was the value of the capacitor in the solution? It's probably slightly different. Lydia, are you able to look at that or not?
Yeah, I'm pulling it up right now. Yeah, that's about right. The rounding's a little bit off, but yeah, those are.
What about the inductor? You get 13.9?
Mm-hmm.
All right, that's how you do this problem. All right? That's if you're inside the one circle, that's how you do it. Now notice what really the elements look like on this one is we got a parallel capacitance, a series inductance, and that's the way you want to do this usually. All right, so you got a parallel capacitance, that's perfect. That means this capacitor will block DC shorts in case you have an offset voltage, and then you have a series inductor, L. That's perfect too, because inductors you want to be, at DC they look like short circuits, and there are reasons, depending on what this is feeding over here, this 100 minus or plus J something, it may be an amplifier that requires a DC offset. Remember when you get an amplifier and you all had your, what is it, the microelectronics course in amplifiers, basic analog, right? You had a BJ, or you had a bipolar transistor amplifier, right? You had to get an offset current in order to get the gain, right? You adjusted that current so you had a voltage at the base about 1/2 the peak voltage, right? Do you remember this? Once you did that, you got an offset current, and then you could say, well, the amplification factor was basically GM, right? And GM is the current I divided by 0.25. You don't remember doing this? And then it's going to be that times the resistance and the load, and that would give you your voltage gain. But I'm not going to go through that with you. Y'all with me? Now this, the reason I'm saying this, at the microwave frequencies, this type of impedance matching network may take an amplifier's output and go to an antenna, or it may take a preamp and go to an amplifier, and that would be the input impedance of the amplifier. You want to allow DC to flow, and you want to block any kind of short to ground. All right, the capacitor blocks the short to ground. The inductor allows DC currents to flow. That's my point. All right, let's do another one. Hey, Lydia, can you get that tool working? I mean, do you have internet?
I looked at it, but I could not figure out how to work the problem.
Do you have, does anybody, William, do you know how
I
to
have-
work that tool?
I have it pulled up.
What?
Yes,
All right,
yes,
why don't you do, huh?
yes, I believe so.
All right, just do me a favor, put Z0 50 in there. We're gonna do this, that's the reason I'm saying. I can pull it up and do it, but I prefer you to, so you can learn how to use it. If you have your laptop here, go ahead, pull up. This is a good thing to learn how to do. You got it up?
Yes, I got it. So-
All right, here's the problem. I got a load, here's my load. It's 0.25 minus J 0. Minus J 0.25. And my Z naught, 25. Make it 25 minus J 25, and Z naught is going to be equal to 50. All right? All right, so here's what we got here. Put a minus, plus, minus. It could be a plus, doesn't matter. And here Z naught is 50. Now I want you to build an L circuit, all right, they're going to match this, right? Really an L matching network. L just means, it looks like an L because it's shaped, one in parallel, one in series. So it's called an L section matching. So where do we start always? What do you always do? That's the impedance, the load, and that's the characteristic?
Normalized.
Yeah, we start with ZL. We find out what the normalized impedance is. And that's going to be simply what? 0.5 minus J, right? Minus J 0.5. You all agree with that? Everybody? All right, now, what do I do next? Well, I'm going to draw, you have Smith charts, rotated Smith charts. I'm going to draw one, try. And here's the rotated, my rotated. Rotated. All right, so when I plot this point, 0.5 minus J 0.5, where is it? Well, I know the 0.5 circle is here, right? Something like that, correct, class? Just take a look. Now, where is J 0.5? Somewhere out here, right? Do you agree with me?
Mhm.
So is that point inside the circle or outside? I'm actually not sure.
It's outside
Is it outside?
of the.
It's on the
Oh.
rotated circle.
It is on the rotated circle?
Like
Yeah.
exactly.
Yeah.
Oh, then that's money. All right. So if we take this, and we're going from, when our normalized is right, so it's minus, what is the value? Hold it. That is right here in the rotated?
Yes. Yes.
All right, so that's ZL. It's on the rotated circle. Here's the thing. We just have to go to the admittance domain and go back here. Y'all follow me? If we're right on the rotated, that's ZL, right? We go to the admittance domain. What do you get for the point here? Wait a second. I drew that wrong. This is ZL down here, isn't it?
Yeah, this
Sorry, this would be 0.5 minus J 0.5. That point right there is not right, so this is 0.1. And then when we go like that, when we take the inverse of that, we get this point, that would be 0.2. Now we're in the admittance domain. What value is it? 1? What? Better have 1 there, minus J or plus J something. Just J1? Is it J1?
yes.
1 plus J. Oh, so that's out here, right? Is it? That's already 1, and J is up here, so it's about here, isn't it? Roughly, guys, can you see it? 1 plus J. J? All right, so if that's the point here, this, I got it drawn on it. This point here, somewhere here, will be 1 plus J1. All right, so what do we add? Now we're in the admittance domain. Class? We want to get rid of that J1, right? What do we add in parallel?
Capacitors.
If we add a capacitor, and we can do this, what happens? It's not a capacitor, right? Well, maybe it is. Let's see, we want to get rid of this J1, so this is the admittance domain, correct, class? If we add a capacitor, we'd be adding positive J, right? We would actually want to add an inductor. Y'all follow me? But it would be in parallel. This is not a good design. So this would be some inductor, but we got to figure out the value. So this is admittance, and I have an admittance of 1J, that's normalized. I want to get rid of it, so I want to add a minus 1J. Do you agree with that? So actually what I want to do is find minus 1J, and I want to find the value of the admittance, or the component. But I've got minus 1J, and that's equal to, well, I start with the normalized impedance of an inductor, or just the impedance of an inductor, is J omega L. Then I divide it by Z naught. Now that's the normalized impedance of the inductor, right? The admittance of the inductor is 1 over that. And so Y of the inductor would be equal to Z minus J, right? Z naught over omega L. Do y'all agree with that? Just think about what I'm doing. I took 1 over the normalized impedance to get the normalized admittance of an inductor. It's got a minus J, right? Y'all with me? I have to set that equal to this. So I have minus J Z naught over omega L here. And that means when I calculate the value, this is one element that's going to match. That would be in parallel for L. It would be L is simply equal to Z naught over omega. And if we let F be equal to 10 to the 9th, we might as well do that 10 to the 9th hertz. It's going to be 2 pi times 10 to the 9th here. Now, what do you get for a value of L? Now, this isn't the ideal way to do this. I'm going to talk about that in 1 second. Anybody?
The calculator's saying 7.95 nanohenries, but I could put it in wrong easily.
For L?
Yeah.
Anybody? That would be Z naught is 50, right? 50 over 2 pi times 10 to the 9th, so it's 50 over 2 pi nanohenries, whatever that is.
I think it comes to the 9.
Is that right?
Oh.
Can't be 8 by itself, right?
Oh, it's 7.9577 nanohenries.
7.9577 nanohenries would be the inductor, and it would be impedance match. What's the problem with that design?
Inductors in parallel.
Yeah, you don't want that generally, all right? Because if you're feeding an amplifier with that, that'll short all the DC current. So what's an alternative way to doing this? Well, when we looked at the, first of all, in the impedance domain, the normalized impedance is 0.5 minus J 0.5, right? Correct, class? Now listen, that's impedance right there. What's the admittance of this? I'm just gonna, hold it. Okay, yeah. What's the admittance? Take 1 over that. It's 1 minus J1, or 1 plus J1, right?
Yes. Yes.
All right, that's the normalized impedance right here. Now listen. If we added an inductor in series, remember this is impedance, right? It's normalized. So if we added an inductor in series, we would be adding plus J something, right? And we could go right to this point here, right? Y'all follow me? Then we would have the same magnitude, 0.5, But this would be plus J 0.5. Do you all agree with that? If I add it, I'm just going to get rid of this and turn it into a plus J.5. See if that point isn't on the rim right there. Y'all see it? I call it a conjugate point because the imaginary term just changes sign. All right, now that's adding an impedance, right? It's normalized. How much impedance do we have? This would be a series element. Impedances are always in series. I went from minus 0.5 to plus 0.5. I added 1, didn't I? So that means what I'm going to do, forget this design. This design, it'll work, but it's not going to work for every situation. What I'm going to do is add something here, an impedance that's got a value, a normalized value of J1. That's the normalized impedance, right? That would be an inductor. So I would say that the impedance J1, which is normalized, you all follow me while I'm doing it, is equal to, well, it's a plus J, it's an inductor. So the impedance of an inductor is J omega L, right? To normalize, we divide by Z naught, correct? Now that means we could find the value of the inductance equal to Z naught divided by omega. And what do you get for that value, by the way? Anyone?
Literally the same thing.
Yeah.
Is it the same? Okay. Oh, yeah, yeah. All right, so this is going to be this value that's now in series right here, right? Correct, class? Now that's the impedance domain, right? Now we go to the admittance domain, take 1 over that, and what do you get?
1 minus J.
This is 1 minus J1, right? Right. Isn't it, guys? That's the admittance domain. Now we have to add something in parallel, an admittance in parallel to get rid of that. And what's the admittance going to be? If it's 1 minus J1, we have to add plus J1 to get rid of the negative minus. So we're just adding J1 right here. And that's it. So we got the value of the inductance, which is 7.9577 nanohenries. And what's the value of the normal, if that's the normalized admittance, what's the value of the capacitor?
I got 3.18 picofarads.
Yeah, we know that the normalized first capacitive reactance is 1 over J omega C. Right? Normalize it, it's 1 over J omega C Z naught. Everything's downstairs. 1 over that's the normalized admittance, which is J omega Z naught C. And it has to be equal to 1. So we have omega Z naught C equal to 1. And therefore C is equal to 1 over 2 pi times 10 to the 9 times 50, right? And I don't know what that is, but
3.18 picofarads.
is that right?
Yeah. That's what I got in the website and in my calculator.
3.18 picofarad?
Yeah.
Okay.
Or times 10 to the
So
12.
this is C equals 3.18 picofarad. You understand the reason I did that is because I didn't want to have an inductor in parallel. And that's 99% of the time you never want that. You want an inductor in series and a capacitor in parallel. This inductor in series won't stop DC currents, and the capacitor in parallel prevents shorts down the ground for DC current. That's what you want. One thing just to mention in passing here, whenever you put a capacitor in parallel with the line, check the actual breakdown voltage, because if you've got high power microwave stuff, that voltage, you got to make sure your capacitor won't short out, because you can get a high enough voltage will just arc right through a capacitor. You got to make sure your capacitors have enough breakdown strength so they don't blow.
I was gonna ask because if it did blow, then it would just be like an open wire.
Whenever you short a capacitor, generally speaking, when it goes on failure mode, there's 2 types of failure. One is something that's going to heal, and that is oil-filled capacitors. All right? Like if you have oil-filled, if they short out after the short's done, unless they rupture and thermally heat and then they blow up, what'll happen is they're healed, it's self-healed. It's back to normal with oil. But if they're any kind of a solid material and you get arc over, it's trashed. It'll never be useful again because either there's a burnt cord there, it's a short, or that rupture there will destroy the actual value of capacitance and change it. So that's, and by the way, with electrolytic capacitors, when you destroy those, when they arc over, or when you drive current in the wrong direction, they blow up. I mean, they're like bombs. So, I mean, I had an electronics shop when I was young, and these are not some of the, I don't know, there's some characters in there. They take capacitors, they put them in a wall, and the voltage up, and then turn them on and watch them blow up. And electrolytic capacitors, they blow up in ways that are pretty serious. Anyway, don't do that, but I'm going to tell you, I've seen this kind of stuff, and it's not generally something you want to happen. All right. Now, another one. All right. So far we've gone, and that one was on the rim. I was trying to do it something inside the one circle, but you see the principle, right? All right. Now, if we're outside both, it doesn't matter what we do, one or the other. Let's pick a one when we're outside both. So just think about this. I'm going to just give you the normalized values. I'm not even going to bother normalizing. You know, this is the one circle here. And this is the rotated circle here. And we know J1 is here, right? This would be minus J1. And you all know about that, right? This is a standard Smith chart. So now we're going to take a look at what happens if we're outside the rotated and the original R1 circle. Suppose we're here. Find me a point here that's normalized.
0.2 plus J 0.8.
0.2 plus J 0.8.
Yes.
All right, we're going to label that Z normalized of the load. All right, and I'm just, is it about?
Yeah, it's like right there. No, you're right. Yeah.
All right, that's 0.1. That's in the impedance domain, right? Now listen carefully. We had impedance, it would be a series element. So here's our load. I don't care what the load is, but normalized load is 0.2 plus J 0.8. Now just think about this. Leave Z naught be equal to 50 ohms. I want an L section matching up. Now, you know the 2.2 trajectory does this, right? You all see what I'm doing here? Right? No matter what I do to get rid of that imaginary, I can add plus or minus, or I can add minus J. It's still 0.2 is the real, right? So you don't have the 1. You always want to go to 1, right? The minute you're on the road, on this circle with an impedance or an admittance of just 1, you're right at the center, your impedance matched. Do you follow me? It's 1 plus J 0. That's the center of the circle. Doesn't matter if it's an admittance or an impedance. They're the same when they're normalized at the center. You all see that? All right. So no matter what we add in series, we cannot get to this one circle. Just can't. Because we're always going to have 0.2 for the real part. Y'all with me? We want a real part of 0.1. So what we do is add something. Now, a couple ways to do this. If you think about this, let's go to the admittance domain. Let me do this. Actually, tell you what. I said something. I'm gonna backtrack here. We could do this. We could move along this trajectory and hit this point. Remember, that's 0.2, or this point, right? This is actually the best way to do it. Now, if we're moving along this trajectory, we're adding a series value. Do y'all agree with me? So if we move to here, what value would we add? Can you tell me? Get on that and go down here, the 0.2 circle, and see where it intersects the rotated circle.
It's going to be 0. I'm sorry. It's going to be 0.2 plus J 0.4.
How many see that? Right? We were at J.8, this is impedance, right? We want to go to J.4, what do? Subtract J.4, right? That would be an impedance. Do you all agree with that? So if we did this when you do this in your thing, if you just put a load of 20 plus 40 ohms and Z0 is equal to 100, you'll get this in that program, right? Because then the normalized would be 0.2 plus J.4, right?
Isn't that going to be adding a capacitor in series?
It is. And I was going to get, I'm going to get to that. You're ahead of me. I'm just showing you a possible design and why you wouldn't want it, right? Hang on to that thought. You're ahead of me on this. I still got 5 minutes. Well, not quite 5 minutes. Anyway, so if I add that, I would want a capacitor in series. I'm going to go ahead and put it in because he's right about this. In series, now we need the value. Well, we want the capacitive reactance to be minus J.4 normalized, right? So I have capacitive reactance is minus J over omega C normalized. The normalized impedance would be Z0. And that has to be equal to minus J 0.4. Does everybody understand where I'm getting at? Right? Because if I add that value to the original value we had in series, I'm down to J.4 and I'm on the rim of that rotated circle. So if I do that, what do you get for C? Well, C would be equal to what? C would be equal to 1 over, just think about this, multiply by C, divide by 0.4, you get 0.4 times omega times Z0 would be equal to C. Do you all agree we can calculate that? All right, you give me an omega Z0, we got it. Now we find that C. Now we're here, right? We're still in the impedance domain. When we go to the admittance domain, what happens? We're on the rotated circuit, right? It's admittance. We're going to get a value, and I don't know what value we're going to get, but I got a feeling it's going to be it's going to be 1 minus J something. 1 minus J2. Anybody confirm that? All right. Now, that's admittance, right? How much normalized admittance do we have to add to get rid of this? J2, right? So, that's normalized admittance. Think about it. Anytime you see a positive J, you know it's capacitance. So the admittance would be J omega C normalized would be Z0. This is for the capacitor. We're putting in parallel. You all agree with me? And that's equal to 2, J2. Or we can say C is equal to 2 over omega Z0, and that is the capacitive value. But you brought up the point. If you don't want a capacitor in series, what other options are there? Here's where I want you to start thinking. Because remember, we can do this problem a whole bunch of ways. When it's outside the rotated circle, you can do this 3 or 4 different ways. Now just watch this. So, I'm trying to erase this without recreating the circle. Now when I look at this thing, suppose I have the original point William told me is 0.8, right? Plus J 0.
It was 0.2 plus J 0.8.
0.2 plus J 0.4. I'm sorry, right?
8.
0.8? I'm
Yes,
sorry.
yeah.
0.8. 0.8. Right? That's the original point. That's impedance. All right. If I go to the admittance domain, pick 1 over that. I don't know. It's outside the 1 circle, but I don't know where it is.
Zero 0.3 minus 1.18.
Minus J 1
Yeah.
point what?
1.8.
And that's outside the 1 circle, right? Classic. All right, now that's admittance, right? Now just listen to me. If I add or subtract admittance, I can get rid of that component, but I want to see what I'm going to do. Remember what I've done. I started at that point. Now I'm going to add something in parallel. Just listen to me now. So when I'm in the admittance domain here, I travel along this trajectory. If I'm adding plus j something, well, first let me ask you this. If I go on the 0.3 trajectory, which is going to be something like this. So if this is 0.3 minus j 1.1, this is 0.3 real, right? Can you all see that? There's 2 points that intersects this circle over here, the rotated circle, right there and there. Do you agree with this, class? Go ahead and draw it. See? Do you all know what I'm talking about? Jake? All right. What's the first point?
It's going to be 0.45 plus j, or minus j1, right?
Minus j what?
Wouldn't it be 1? Minus j1? Because
Where?
it's at the, oh no, no, sorry. It's at minus j 0.25.
Can everybody confirm that? Guys?
Or wait.
You see, this should be 0.3, right? It has to be 0.3 because this is 0.3. We're moving on the 0.3 line. Y'all follow me?
Yeah.
See, this is 0.3, so when we're moving, it has to be 0.3 minus something.
Look away. It's minus j 0.45.
Can somebody confirm that?
Yeah, I just had it flipped, sorry.
That's all right. And my eyes aren't real good when I'm reading some of these things. I have to get a magnifying glass. Y'all with me? All right. We ended up there. The other one would be what? That same point, only plus j. It'll always be the same point on the sign and flip on the legend. 0.3 plus j 0.45. All right, now here's my point. We're adding here an admittance. Do you agree? Start with impedance. Now, if we're adding an admittance, if I add an admittance and get to this point right here, it would still be a capacitor, right? Because it's a positive value of j, right? I've got 1.18 negative. I want to get to 0.45 negative, so I subtract 0.45 from this, and that would be the amount of the positive j, right? That would land me here, correct? Now listen carefully to this. I'd be adding a capacitor in parallel. But when I go from here, I'm on a rotated circle to here, now I get 1 plus j something, right? That was impedance, admittance. Now I'm back to impedance, right? If I have this and I get a plus, do you all agree this will be a plus j something, right? This would be impedance. Plus j means I got to add minus j. That would be a capacitor. Do we want that? This is in series, all right? This would be impedance. We don't want that. So what do? We move from here all the way to here. Because now we have 0.3 plus j 0.45. You agree? Take 1 over that, and now we get a negative value. We get 1 minus j something, right? Follow me? And it's in series, well, I can add an inductor to get rid of that negative j business. Do y'all follow me on this class? How many do? Lydia, with me? So remember, we want inductors in series, capacitors in parallel, and nothing in between. And that's the moral of the story. I ran long today, I'm sorry. But I hope that answered your questions. Do you have any other questions for me about this? Y'all follow me on this stuff? I can give you